Hi, today I want to explain more about bioinorganic chemistry. Dr. Azad Mahdi. I just found from my database that lots of information would be essential for my presentation or my videos, and to the benefit, of course, of people who listen to me or my videos. So bioinorganic chemistry, of course, it's a mix of biology and inorganic compounds. So everything in the biology based on chemistry. What type of chemistry? So it involves mainly transition metals and as the core center of the biological molecules, which they are giant super molecules, and the central metals or one metal is related to transition metals or even the metals. So we are dealing with inorganic compounds. So bioinorganic chemistry, highly interdisciplinary research field. You can see here bioinorganic chemistry covering or biochemistry, microbiology, physics, toxicology, toxicology, pharmacology, physiology, and inorganic chemistry. So all of them, they are all related to bioinorganic chemistry. So bioinorganic chemistry, study of metal ions, chemistry in biology, the roles played by metallic elements in biochemistry is in metalloenzymes, which an enzyme required the participation of a metal ion at the active site to function. So enzymes, metalloenzymes, they are catalysts, speed up reactions, and very important to make reaction done and at time consumed. So the role of the metal atoms in enzymatic catalysis, currently active subject of research. So if we come to bioinorganic chemistry, chemist needs to understand the role of metal ions in the maintaining healthy life, as well as health problems associated with overload of trace elements. For example, the design of metal chelates with biological activity that could administrate in deficiency or excess of certain metals, or removal of poisons via chelation therapy, like in the treatment of Colles anemia, which is overload of iron in the tissue, or Wilson disease, which is caused by overload of copper in the liver. Okay, so now we have to use bioinorganic chemistry to understand the role of metal ions. Why metal ions? Metal ions very important to maintain the healthy life and to remove bad stuff from the body, so they can chelate, they can bond to these poisons, metals, or other bad we call them substances in the body, so they can chelate with them. So metal ions are very important. When the scientists examine some of the simplest life exist as microscopic single-celled organisms, he finds the compound of which they are composed are the same order of complexity as those found in the higher organisms. So I quoted this from John Rand Tim, this book in 1966. So, okay, so microorganisms, they live similarly to the higher order of other organisms like human, animals, elephants. So simple micro single cells organism, they can function similar to the higher organisms. But here the mechanisms by which such compound came into existence from inorganic matter is still unknown. The mechanism, we always want to know how this happened, how these materials produced or react. So we need mechanisms. We need to stop at the steps took place to produce such function or such materials. So many interesting theories have been proposed. If we come to the biology and see, we have about 30 elements are recognized as essential for life. It's about 30 elements essential for life. Some required in bulk or at least macroscopic amounts. They integrate in all forms of life, such as hydrogen, sodium, potassium, magnesium, calcium, halogens, oxygen, phosphor, sulfur. So all of them, these are important. The others occur in trace quantities, like iron, copper, zinc, which are the top end of this trace scale and are apparently also essential to all. So even if you have in bulk, in a big, huge amounts, or you have in traces, so concentration, very important for life. So the remaining elements that are required, at least few life forms, are lithium, boron, fluoride, silicon, vanadium, chromite, manganese, molybdenum, tungsten, you name it. So the others are remaining elements for other forms of life. One of the major roles played by metallic elements in biology is in metalloenzymes. So metalloenzymes, when you link the enzyme with the metal, it will be metalloenzymes. This term applied to enzymes not only require the participation of metal ion at the active site. So I put the active site in red because this is the main core of the life of that organism is the enzyme, which is a protein and active sites. So how the active site is functioning, or how does it bind to the metal ions, even for the ground state or stable state. So the known metalloenzyme now number several hundreds. The role of metal ions in enzymic catalysis is very active in research, catalysis, enzymatic catalysis. So a study of the chemistry of metal ions of biological interest is generally carried out by using naturally occurring or synthetic model compounds that mimic or similar the properties of those existing biological system. So now there are some natural occurring and there is synthetic occurring or making models for the nature is important for bioinorganic chemists. So in an attempt to discover new models, important natural occurring compounds and reactions, the application of advanced inorganic techniques to biological process has led inorganic chemists to understand the roles played by these metals. So two main groups of metal ions involved in biological system. First group consists of ions such as sodium, potassium +1, magnesium +2, calcium +2. So these are the four, or the first group, very important, which occur high concentration, making up approximately 99% of the total metal ions content in the human body. So human body can be made of, magnesium, calcium in the bones, and you have the potassium and sodium, very important in the cells. So potassium outside the cell, sodium inside. So they have to be regulated or equally present in the body. These help maintain the structure of proteins by neutralizing the negative charges of peptide chains, then control mechanisms of cell membranes. Okay, so these are the structure of proteins. So structure of proteins can be neutralized by negative charges, peptide chain. So when you have negative charge, you need these positive charge ions to bond and control or to be exist. The second tab comprising of ionic form, iron, vanadium, molybdenum, cobalt, nickel, copper, and zinc. These are found in proteins. Binding interaction is strong and not easily broken. So we can find these in the proteins. Iron, you remember iron, where we can find iron in hemoglobin, zinc, you can find it in the brain and others. So these proteins can subdivided into proteins which generally function as either storage and transport or metalloenzymes. So we have proteins now. These proteins consist of these metals and very important. So let's come to transport and storage proteins as oxygen transfer, like hemoglobin, electron transfer like cytochromes family, management, metal concentration like ferritin. So all of these are in transport and storage. Transport of oxygen, hemoglobin, and myoglobin. You have a transfer. So these are the storage of oxygen, even to carry the oxygen. And you have cytochromes as well. You have ferritin, which manage the metal concentration. So iron, special important transition metals in a human body, which stores surplus, excess of iron, releasing it when necessary, and belongs to class A. Metalloenzymes, which consist of a third of all enzymes, include oxidoreductases, nitrogenases. So these are metalloenzymes of third of all enzymes. We can see them as oxidoreductases, nitrogenases. The nitrogenases involve the vanadium, molybdenum, iron. And we have a group of hydrolases, which like carboxypeptidases, zinc, and isomerases. We have vitamin B12 coenzyme, which involves cobalt. So hydrolases, they're carboxypeptidase like urease, which involve nickel. Let me add this one. Example, you have ureases, nickel, carboxy peptidases. There are zinc, zinc and isomerases. We have vitamin B12 coenzymes, which involve cobalt. Biological ground ligands, including. So let's come to the ligands, which we understand that from the inorganic side. So we have in biology we have proteins. They are biological ligands, carbohydrates, lipids, steroids, nucleotides, prosthetic groups, coenzyme B12, blue mycin, siderophorus, and complex assemblies. Now, many inorganic elements are essential for life, as we said. Organisms make economic use available resources, but also have developed mechanisms, but also have been developed mechanisms to accumulate certain elements. Despite of low amount of metal ions presence in living systems, they are enormously important for virtually all life processes. Both deficiency and overload excess lead to illness if there is a deficiency, or overload, so they can lead to illness. So synopsis of important properties of metal ions. We have to look into the geometries and electronic structures of metal ions in biological system. We need to understand the thermodynamics, which complex stability, side selectivity, or we can like stability, charge, ionic radii, Irving-Williams series, other effects, pKa, the value and competition of metals with protons. So we need to look into properties important of catalysis, like Lewis acidity, redox, ligand exchange rates, and then the effect of metal environment created by protein. So if we come to the general properties here and of the sodium potassium cations, we can see a predominant oxidation state +1, stability very low of the sodium and potassium. So prefer donor atoms is prefer donor atoms, yeah, and you have mobility in biological system is high. Magnesium +2, calcium +2, their oxidation state will be 2+. Their stability will be low or medium. And the mobility in the biological system will be medium. Whereas zinc and nickel +2 in 2 oxidation number are very high stability. Okay, so the donation or the preferred donor atoms is from the nitrogen and sulfur side, whereas in magnesium and sodium will be oxygen side. And then they are low to medium, especially for zinc, which is the mobility in the biological system. And now you can see such, we expect stability of the iron. Everything is being studied, and the geometries are important. Which metal can prefer which geometry? So, and what type of spin with oxygen and nitrogen donors? Is it a small, high spin? So preferred geometries in small high spin complexes with oxygen and donor nitrogen. So the copper 2, which is D9, as you know, copper 2 is what the copper itself is for it comes to 4s2 3d9. So losing 2 electrons will leave d9 in the outer shell. So copper 2 prefer tetragonal 5 coordinate or tetrahedral. Manganese 3 prefer D, which is D4. Copper 1, now D10 is always linear, trigonal, planar, or tetrahedral. And so on. If we come to the lower, okay, let's go to the zinc. Sorry for that. We come to the zinc here and cobalt. So the cobalt D7 prefer octahedral, tetrahedral. Zinc 2, D10, tetrahedral, octahedral, 5 coordinate. But the range of iron 3, cobalt 3 until manganese 2 and nickel 2, they prefer octahedral or others, where you start from like D3, D5, D6, D8. So ligand field theory and steric factors are important. Oxidation states here, if you see common in chemistry, which is in the circle, empty lines here or figure, you can see from +1 to +7. So potassium is a +1, which is common in chemistry. Calcium, scandium, titanium, but chrome, manganese, and iron, they are oxidation number is here, and you can see the less common in chemistry will be cobalt, whereas oxidation number is 1 + 1. Nickel +1 + 3, it's less common. The not available in to biology when there is like titanium oxidation number +2 + 3, there isn't. Vanadium +2 is not available. Chromium +2, +4, 5, 6, they are not common, and the rest you can see. So common spin states of metal ions. So manganese prefer and when manganese is +2, so it's a high spin D5. So you know manganese will be 4s2 3d5. If you come to losing 2 electrons, remaining d5. So d5, if spin will be, you have high spin, you introduce the T2G and EG singly in all 5 suborbitals. So 1, 2, 3 go up, 1, 2. So this is the high spin, and preferred by +2, manganese +3, high spin D4. You have the everything here. Iron prefer low spin or high spin in D6. But iron 3 is a preferred high spin D5, and so on the rest. Stability aspects, thermodynamics of metallic binding. Important to understand metal uptake and distribution. So how can the metal be uptake by human, by animal, by plant, and how being distributed along the body? So specificity of metal binding, we call it biomolecules. How specifically is binded in which side? Catalysis by metalloenzymes. So metalloenzymes speed up the reaction. They are as catalyst. Interactions of metal ions with nucleic acids. So we have interaction as well of these metals with the acids. So stability constants here, if you take L or ligand plus metal, it will make ligand metal. So what's the uh, constant K? It depends on the concentration of the products divided by multiplicity of concentration of ligands and metal. So we expressed as a log K. Log K, if you know the K, if it is 10 to the power 15, so the log K is 15. So we have dissociation constant KD is what? K minus 1, which is log KD. And this is equals to minus 15. So that's how we express the stability constants. So rough rule of thumb, strong complexes, log K bigger than 10, and the weak complexes log K less than 4. Stability aspects which govern the stability is first is charge effects. So the higher the charge of the cation, the more stable of the complex. The high charge of the cation is the metal. So the metal lost electrons. How much losing electrons? More electron lost. It means the outer shell will be almost stable by losing even all electrons to become like a noble gas, more stable. Biophysical reason, charge recombination is favorable. So when reorganizing the charge, this is favorable. And then there will be H sub principle. So second effect is the stability will be the ionic radii, which depends on position in the periodic system, the charge, which is charge higher, smaller, and coordination number. Is it like 4, 5, 6? How many coordination number you have? How many bonded ligands to the metal center? So if covalence, so that's due to the differences in electronegativity. So if you go with the covalence of electrons, you see which electronegative is bigger than the other, and to see the affinity or sharing or of the bond. So steric hindrance in which direction is moving the reaction. So that's important. ZR charge radius, how is the relation between the charge and the radius of the atom, which dictate order of stability. So only with very small ligands, example, halogen, fluorine -1. Hard and soft acids and bases. We have terms hard and soft acids or bases. So the hard acids, such as proton, hydrogen, sodium, cations, potassium. So these are the hard acids. Acids mean they lost electrons. And the bases, they gained electron. They are very hard, which is ammonia, amino group, water, hydroxide. You have oxygen. You have hydroxide, alkyl, oxo, alkyl, carbon dioxide, or carboxylic acid, RCO2, phosphate. These are always, they gained electrons, so they are hard bases. So we have borderline, like imidazole, like you have aryl NH2, so amino related to a group of aromatic group, aromatic NH2, and imidazole. They are borderline, they are in between. And you have iron 2, cobalt 2, nickel 2, copper 2, zinc 2. But the soft acids are what? Copper 1, silver 1, orate 1, platinum 2, lead 2, mercury 2, cadmium 2. These are soft acids, and the soft bases are thio group, either with one alkyl or two alkyl group. So hard and soft acids, we can see with the range between the Z and R, the atom and the radius relation. And here you have from 800 to 2600. So that's the percentage of iodine, sorry. And we can see the range of hard, soft acids being distributed along the chart. And we can see magnesium 2 is the hardest one, and the soft will be the lower: mercury, lead, platinum. And we have in the middle is the borderline. Irving-Williams series, stability of high spin divalent metal ion complexes. So this is the Irving-Williams series, which one is depend on the atomic number, and the log K for addition of the first En. So now you have always peaks at copper 2. We can see the copper 2, the highest peak here, and the depends on the ionic radii and ligand field stabilization energy, LFSE. So you can see the highest is copper 2, and there will be chromate 2 as well. Stability aspects interplay between these. If we come to H sub principle and the Irving-Williams series, and you can see here log K opposite to the iron and copper, or these atoms here, and the increase with the log K is, what is it? Is it NN, NO, oxygen, thionitrogen? So everything here with the presence of the metal, how can they bond it to the which side of the ligand? So if we see here, the high spin metal 2 complexes are bidentate, and there is a trend more pronounced the softer the ligand. Competition with the protons. This is as well depend on the like the stability of the of these compounds. So both metal ions and proton hydrogen positively charged. The metal ion and the H plus are chargedly positive and have affinity for bases. So they always eager to bond to the base. The actual concentration of the complex metal ligand therefore depends on the concentration of metal and the ligand, and the hydrogen, of course, concentration. So actual concentration of the complex depends on concentration of metal and ligand, and at the same time is the proton hydrogen. So the low pH, you know, minus logarithm H, concentration of H is the pH. The low pH will go to the higher pH. So that's Ml complexes dissociative or dissociate. When from low pH to the higher pH, the Ml complexes dissociate. So effective apparent or conditional stability constants. Competition between protons and metal ions, proton hydrogen, of course, which is for the 4 most common zinc ligands in proteins. So calculated with the log K equals to log K plus log Ka minus log Ka plus concentration of proton. So here the log K from 0 to 10, this pH from 0 to 12. So now you can see the glutamate, aspartate, which is bounded by nitrogen, oxygen, both of them. They increase the log K with increasing pH until they reach to a point there is no more increasing in the log K. Whereas this histidine is behaving similarly, reach to the point, and then whatever the pH is, they are stable with the log K. But the cysteine, which bind by S and N, bidentate, this amino acid is increase all the way till up to 10 and 12. So here, if you come and values for the log, for the 1,1 zinc complex is taken from the UPAC stability constant database, minus log Ka, which is the constant of the acid, equals to pKa. So for the cysteine, 8.5, and for the histidine, 6 to 7, aspartate glutamate will be around 4. Other contribution to the stability is chelate effect. So how they chelate, how they bind to other metal. So what the preferred coordination geometry you have? Dielectric constant of the medium. Interiors of the proteins can be very different from water, usually more hydrophobic, which result to the lower dielectric constant, enhance the charge recombination and therefore complex formation. Catalysis in metalloenzymes, very useful, important. The property of metal ions exploited for the enzymatic catalysis and dealt with the Lewis acidity, Lewis's affinity for electrons, polarization of substrates to facilitate attack by external base, and then increase attacking power of bond base. pKa related to Lewis acidity. pKa, acid, this is the constant. P, stability constant of the acid values, coordinated ligands are lowered. So the aqua ions, pKa usually 9 to 10. In zinc enzymes, low as 7. So the aqua, there is a water ions. The pKa usually between 9 and 10, but with the zinc enzyme will be 7. You know what is 7? It's in the middle. So orienting the substrate and stabilizing it in the conformation conductive to reaction and then redox activity. So we have the properties of the metal ions. For the enzymatic catalysis, we have to look into the Lewis acidity, orientation, and redox activity. And then Lewis acidity, the effect on pKa of bound ligands. You see here the pKa for the ligand and reaction. When there is a water with the metal ion, the water lose proton hydrogen to produce metal hydroxide, and there is one positive charge. Okay, if you add proton hydrogen you will end up with water. And so either this is oxidation, or you come back to do reduction. So here the metal ions, the pKa being checked at room temperature and 0.1 molar concentration. For the calcium at the top, +2, pKa measured at 13.4, zinc at 10. But when there is ammonia with the metal ion, such as cobalt 2, copper 2, nickel 2, you add ammonia, you will deprotonate the NH3 to become NH2, and the pKa measured 35 up to 32. When you have a carboxylic acid reacted with the metal ion in the oxidation state 2, losing one proton, you will end up with binding one or monodentate to the metal. Okay, let me say this. So there is a monodentate between the carboxylate after this hydrogen being deprotonated, lost. So the oxygen will bind singly to the metal ion. And here, when you check with them in case of magnesium 2, you can see very low pKa 4.7 for the copper 2, 3. If you come to the imidazole plus metal ion like cobalt 2, nickel 2, copper 2, you deprotonate one hydrogen, and this nitrogen will be singly bounded to the metal ion. So losing one hydrogen, and then the metal will be +2, and you can see will come from cobalt to 4.6 and 4 and 3.8 respectively, and these data have been obtained from Lippard group and Berg. So hydrolysis of the aqua complexes, these are the hydrolysis, losing proton in the presence of water, ammonia, carboxylate, imidazole. Importance of redox chemistry in biological systems, electron transfer reaction energy generation for life is based on a flow of electrons. It's like from fuel to oxygen respiration. So the fuel in the body is what is from the respiration. We intake oxygen. That's the type of energy we produce for the cell to burn the food and then produce energy. Standard reduction potential, pH 0. So there are copper +2, copper +1, the electron volt, 0.1, it's endothermic. And you have manganese 3, manganese 2, 1.5, until you come to exothermic is oxygen, oxygen minus 33 volt. And if you have the case of hydroxide with the proton, the case of the water species, so it's a 2.3 electron volt. So oxidizing power increases from the top to the bottom. Redox potential of metal ions are highly dependent on the environment and coordinated ligands. And you know the pH 7 is minus 0.4 volt. And when there is a proton and to hydrogen or oxygen to hydroxide, plus 0.8 volt. Now, kinetic aspects. The kinetic, the rate of the reaction, water exchange rates. So lifetime of complexes useful to characterize reactivity in ligand exchange reaction. And you have here some kinetically inert species, chromium 3, indium 3, and aluminum 3, beryllium 2. Here in the middle, you have species, but here cesium 1, rubidium 1, barium 2, maybe mercury 2. They are labeled all these magnesium, lanthanum, zinc 2, nickel, cobalt, iron, manganese, copper 2. All of them, they are labeled, they are fast in the reaction. And when you say inert, inert means when the reaction takes less than a minute, will be finished. This will be inert. More than 1 minute, the reaction will be fast. Proteins tune properties of the metal ions. Coordination number, very important. The lower coordination number is the higher Lewis acidity. Coordination geometry. Proteins can dictate distortion. So protein can distort the geometry. Distortion can change reactivity of the metal ion. And there is a weak interaction in the vicinity. So second shell effects, hydrogen bonds to bound ligands, hydrophobic residues, dielectric constants can change stability of metal ligand bonds. So we will look at these in more details. Summary, you have the behavior of the metal ions in the biological systems can be understood by combining the principles of coordination chemistry with a knowledge of the special environment created by biomolecules. Thank you.